Hi everyone. In this video, we're going to continue the unit on interlacing, and we are going to actually start the formal treatment. Right, just as a recap, in the first video in the unit of this unit, we saw how interlacing comes up when you do rank 1 updates. It was just a, for example, we won't need any of the results there, but I think it was quite insightful to see, so it's worth your time. Then in the second video of this unit, the previous one, we actually saw the geometrical interpretation of what's happening, behind the scenes when you do and work with real-rooted polynomials. So we saw this double root manifold that somehow tells you that when you don't cross it, the max root function is nice. We stated some facts, theorems, we didn't prove them, and in this video, we're actually going to do the formal treatment. We are going to prove a variance of those facts. It will be more easily used in our setting, and so we are going to actually prove 6 lemmas. 2 of them will connect real-rootedness and interlacing. One of them will tell you what was actually a fact from the previous video, namely that the max root function behaves nicely when you look at 2 real-rooted polynomials whose entire segment connecting them doesn't cross the double root manifold, which in terms of interlacing would mean that they have a common interlacing. And then there are 2 more lemmas that are kind of more specific to our needs, because we have some specific polynomials in mind, right? The characteristic polynomials of some A plus P transpose, or P is a permutation. So we'll need to somehow say something about these polynomials. And so that's going to be quite a technical video, but I think it's quite intuitive also, especially if you have the double root manifold in mind. And then in the next video, we are going to prove, to finish the proof and actually use what we prove here and prove that our polynomials form what we'll call an interlacing family. So the polynomials are nice enough so that you can kind of connect them by these segments and then find points in those segments that you connect by segments and so forth, while completely avoiding the double root manifold. Okay, so let's just start. Okay, so first of all, let me just make sure that we all have the right definition in mind for what interlacing and common interlacing mean. So say we have 2 polynomials P and Q, real-rooted polynomials, and say of the same degree n. And these are real-rooted polynomials. So let's say that alpha 1 down to alpha n are the roots of P, and same for beta 1 up to beta n. These are the roots of Q. So we say that Q interlaces P, and sometimes we use this notation, but not too heavily, if the roots of Q are interlace the roots of P, so beta n is smaller than alpha n, smaller than beta n, also, and so forth, but also beta n is the smaller one, right? So the roots of Q are to the left, or smaller than to the root of P. And otherwise, P is interlaces Q. And usually it won't really matter. I mean, as long as you have this structure, it doesn't really matter if it goes like this or that, as you'll see. But that's the formal definition. Now, sometimes we are going to have actually quite a lot, not 2 degree n polynomials, but actually P, for example, is going to be of degree n, and Q is of degree n minus 1. That's kind of the subtle difference between what we are doing here and the previous video, by the way. That for simplicity, I stated everything there for the same degree polynomials, but here it would be actually nicer, looking forward at what we'll actually need to have degree n and n minus 1. It's not a big deal, but there is some technical differences. So anyhow, if you have a degree n polynomial P and a degree n minus 1 polynomial Q, then we are going to say that P and Q interlace if the same thing happens, but now beta n is not a root of Q, so the roots of Q are just beta 1 down to beta n minus 1. So we are saying that P and Q interlace if this holds, but we just ignore the last inequality, which doesn't make sense. And in this case, you can say just interlace because it's obvious who's who, right? It's not symmetric anymore. Okay, so that's interlacing. And we are saying that a common, this is this definition now, a common interlacing or common interlacer for two polynomials. Now, these are polynomials of the same degree n, is a third polynomial, R maybe, that interlaces both P and Q. Okay, so either it interlaces from below or from above, it won't really matter. And also, I don't mind R to be of degree n-1, in which case the interlacing is clear, but you don't really need to specify from which direction. So a common interlacing is kind of a general name for all of these things. So a third polynomial that kind of separates the roots. So the first roots of P and the first root of Q are before the first root of that polynomial and so forth. So now here are the two lemmas. They are essentially kind of a lemma in its inverse that relates interlacing and real-rootedness, general lemmas, and these were hinted to in previous video. But let's be specific here. So let's say you have a degree n and a degree n-1 real-rooted polynomials, P and Q. And for simplicity, you need to fix it once. So let's assume they have positive leading coefficients. Okay. And for a number t, we are going to look at this polynomial, P sub t of x, which is just P of x minus t times Q of x. Right? So when t is 0, you get P. And as t gets large in absolute value, you get, in a sense, Q, or at least in the sense that the roots are determined by the roots of Q. Right? You don't mind Q. When t is very large, tqx is kind of dominating P of x, and the roots don't mind that you have the t times something. So you should think of pt of x as, when t is close to 0, the roots of that polynomial are closer to that of p, and when t is very large in absolute value, you get close to the roots of q. Okay. Then anyhow, the statement is that if p and q interlace, okay, so that's the interlacing word, then that implies that for any t larger than 0, pt is real-rooted. So that's actually kind of the double manifold word, right? Real-rooted means for any t, you are on the same component of the induced by the manifold, because otherwise you'll go to complex. You go to complex, and for that you need to go through that manifold. But anyhow, formally, for any t larger than 0, PD is real-rooted, and P interlaces PT. Right, so the roots of P are below the roots of PT. Now that it is real-rooted, you can say that. Now, in fact, I should say that, technically we will like to have these two conditions together, but as you'll see in the proof, if you're willing to if you're willing to omit this condition, this result, then actually this holds for any t in R. Right, so P and Q interlace does imply, there's nothing special about t larger than 0, does imply that for any t in R, PT is real-rooted. We'll just see it during the proof. But it will be nicer to just, because we want this end, and for that end, we actually do need t to be larger than 0. And the reason I'm saying that is because when stated like that, and if for every t in R, PT is real-rooted without this result, then you get a converse. And lemma B is the converse. It tells you that, for P, Q, and PT, as in the previous lemma, if PT is real-rooted for every t in R, so that's what's written here, then P and Q interlace. So, just to recap, from these two lemmas, you can get that P and Q interlace if and only if PT is real-rooted for every t in R, namely not just the segment, but the entire line kind of polynomials that in coefficient space that contains P and Q doesn't intersect the double root manifold if and only if they interlace. Right? That was one of the facts that we talked about. But here it's a degree n and n-1 polynomials. It's slightly different. But I mean, that's nice to have this converse, but actually the way we are going to use lemma A we are going to also like to have this results from, so that's true for when t is larger than 0. When t is smaller than 0, it's just pt interlace p, by the way. Okay, so I hope it's clear. Now let's prove lemma A and then lemma B. So what you want to prove is that if P and Q interlace, then PT is real-rooted, and also that P interlaces PT. And the point is, if you want to prove that the polynomial is real-rooted, then the proof strategy will be just to find the roots. And if you find enough real roots, that polynomial is going to be real-rooted. So let's have some notations. So let us denote the root of P by alpha 1 down to alpha n, and the roots of Q. So we call Q is a degree n-1 polynomial. So the roots are beta 1 down to beta n-1, and they are interlacing by the assumption. And also in these kind of proofs, you can always assume that P and Q don't have a common root, because if you have a common root, you can just divide both of these polynomials by that common root. It won't cause you the problems. That's kind of the technical little that you need to check. I mean, between these two roots, PT will also have a root, so it's the same root. And so you can just assume that they don't have a common root, right? So the picture is, if I draw alpha 1, then beta 1 is always to the left of it, not at it. Okay, so let's see. So let's start by looking at the rightmost, the max root of PT. Again, what I'm trying to do is to prove that PT is real-rooted, so I can't really say max root of PT. But what I mean is that I'm going to find a root that eventually will be turned out to be the max root of PT. Okay. So good. So okay. So let's look at this picture. So alpha 1 is the max root of P. That's fine. P is real-rooted, and beta 1 is to the left of alpha 1. And Q has a positive leading coefficient, which means that Q of alpha 1 is positive, right? According to this picture, right? Beta 1 is the last place where Q meets the x-axis, and so from that point onwards, it just go up because it has a positive leading coefficient, and so Q of alpha 1 is positive. So this means that PT of alpha 1, well, it's P of alpha 1, which is 0 because alpha 1 is a root of P, minus T times Q of alpha 1, and we just said that Q of alpha 1 is positive, so this whole thing is negative. Right here, I'm using the fact that T is positive, by the way. Right, because, and what I said about the if and only if will require a little bit of tweak here, but when T is positive, and because of Q alpha 1 is negative, Q alpha 1 is positive, it means that PT of alpha 1 is negative, right? Now, PT, if you look at it, it has a positive leading coefficient. In fact, it inherits the positive leading coefficient of P because Q is of degree n-1. So like in the case of Q, if at alpha 1 it's 0 and it has a positive leading coefficient, it means that if PT of alpha 1 is negative, and it has a positive leading coefficient, it means that at some point it's going to cross the x-axis, and that's going to give you a root. And therefore, that maybe is a little bit kind of mistaken. I can't really say that the max root of PT is alpha 1, but I can definitely say that PT has a root at alpha 1. Okay? PT has a root to the right of alpha 1 because it's negative at alpha 1. Right? PT looks like this. So somewhere here, it's going to have a root. So saying that is actually quite incorrect because you say a max root, you don't even know that the polynomial is real-rooted. That's what you want to prove. But anyhow, we are going to do the same thing now also for all of the other, what will turn out to be roots of PT as follows. So let's look at the picture first. It will help us deal with these equations. So all I did here was to draw P. That's the yellow one here. You see it has the root in alpha 1, alpha 2, and so forth. And Q is the orange curve. And now PT, right, it's P minus T times Q, and T is positive. So if you want to draw PT, you really need to draw minus Q first, so it will be easier. So this dashed line is maybe not minus Q, but maybe some squashed version of it, minus T times Q for some positive T. And now what is PT? So you just need to kind of take the average between the yellow and the dashed curve, right? Because it's P minus T times Q. So this is the green line here. So the green curve is, I kind of just try to, I don't know if it's obvious, try to make it between this and that all the time. Okay. And okay. So what do we know? So let's take I and add I, an index. I is the index of the alpha root, the ith root of P. So kind of by picture, but you can also easily verify that formally, is that for I which is odd, Q alpha I is positive and Q alpha I plus 1 is negative. Right, you can see it in the picture also. It's right, so Q at alpha 1 is going to be positive because of what we said earlier. Actually, it's exactly what we said earlier. And for the same reason, Q of alpha 2 is going to be negative. And so forth. And so this means that PT at alpha I and at alpha I plus 1 is negative and positive correspondingly, right? Because PT of alpha I, well, it's P of alpha I, which is 0, minus T times Q of alpha Y, but T is positive and Q of alpha Y is positive because I is odd. And so that gives you a negative. And the same here. So PT of alpha I plus 1 is positive. Right, and you can see it in the picture here. So, you look at PT, the green thing, and you see that when you look at alpha 2, it's positive, alpha 3, it's negative, and just going to kind of swap like that. Also at alpha 1, it's positive, but it's very high. So something like this. So whatever, this really means that PT has a root between alpha I plus 1 and alpha I. Right, because it turns negative and then to positive or vice versa, and it's continuous, so it must go through the x-axis, which says that PT has a root between every alpha and alpha plus 1. That was for an odd I, but of course it's the same for the same reason for even I. And so all in all, you found n minus 1 other roots on top of the first one that you found. So you found n roots of a polynomial that has n real roots of a polynomial that's of degree n. So this just means that polynomial is real rooted. Now, also by the picture, you can see that P interlace PT. So that's the second thing that we wanted to prove, P interlace PT. Right, because we said that the largest root of PT, now we know it's the max root, is to the right of the max root of P, and then the interlace like that. Okay. Now, as for the remark that I said earlier about the equivalence of this, about the fact that actually this implies that PT is real-rooted for any T in R, but you just then have to remove that. But that's kind of obvious by the proof. So where did we use the fact that T is larger than 0, right? So we use it all the time, but always in one direction. So here we used it. Actually, here we actually used it because we wanted to say, like P alpha 1, when you talked about the max root, what turned out to be the max root, P of alpha 1 is 0, Q of alpha 1 is larger than 0, and so you need to be positive so that you will say, PT as a positive leading coefficient, so it must have a root to the right. Okay, so that part of the proof, actually, you may want to consider only T, which is larger than 0, but don't worry, we can forget about that part for a second. Here we didn't really use the fact that t is positive or negative. I mean, as long as it's either positive or negative, it's all the same. I mean, what's really important is that these two signs will be different. This is positive and this is negative. It doesn't mind if it's positive when I is add or negative when I is not add. It is important if you want to infer that P interlaces PT, but it's not important if you want to infer that PT is real-rooted. So this by itself, even without the previous part, which seems to require it to be positive, so this by itself tells you that your polynomial PT has n-1 real roots, and then you can actually show, if you want, that the last root is actually to the right, as it should be, sorry, to the left. I'm not sure what you see, but I mean to the left in the x-axis version of the smallest root of P, which what should happen. But also, you don't really have to show that because you can just argue that, PT is a polynomial with real coefficients, obviously. Right? I mean, we all say real-rooted polynomials, but I mean real polynomials with root. So P and Q are real polynomials. They have real coefficients, and therefore, and T is real, so PT has real coefficients. And you just found n-1 real roots. So it cannot have, it has one more root, and it can't be complex because complex roots come in conjugates, they come in pairs. So it must be the case that the last root, which actually we can find easily also, is real-rooted. And by the way, it's to the left of the last root of P, which will tell you that PT interlace P rather than P interlace PT. Okay, so we won't need that remark, but it's good to understand that, especially looking at lemma B, because lemma B tells us the inverse, the converse to what I just said. So it tells us that if PQ and PT are as in lemma A, then saying that PT is real-rooted for everything in R, namely the entire line connecting P and Q, doesn't cause the double root manifold, implies that P and Q interlace. And again, by the previous lemma, this is an if and only if. Okay? So let's see that. Now, this is different, right? I mean, the proof strategy must be different because in the first lemma, you assume P and Q interlace and you want to prove real-rootedness. And to prove real-rootedness, you just need to find roots. I mean, that's one way of doing that. Here you want to prove that they interlace. So the proof is going to be different, and it's indeed going to be by contradiction. We're not going to find roots. So again, we're going to assume that P and Q don't share a root. If they share a root, you can divide by it, by x minus that root, and so forth. And now let's assume by contradiction that P and Q don't interlace. So what does it mean? It means that there is a pair of consecutive roots of P, so alpha I plus 1 and alpha I. I'm using the previous notation. These are the roots of P. And Q doesn't have a root in between these two roots. Okay? So this is the picture that you have in mind. This is one root of P. This is another root of P, the consecutive roots. And we are going to assume that Q doesn't have a root in between them. So, it's either above or below, completely above or completely below the x-axis in this interval, this open interval. Okay, now there are a couple of cases, but let's assume they're all the same. Let's assume that both P and Q are above the x-axis. Because, P doesn't have a root between alpha and alpha I plus 1. These are consecutive roots. So it either lies completely below or completely above the x-axis, and Q, per our assumption, doesn't have a root. So again, it has to be on one of the sides. Let's assume they're all up. So what I'm claiming, and maybe I'll give you a sketch in a second in Desmos, is that when t goes to kind of infinity, as I said, PT is P minus TQ. So this means that only the minus Q or Q will matter. So PT will resemble T times or minus T times Q. And then also when T is very large, you won't have a root at alpha, alpha plus 1, because the roots of PT when t is very large are close to the roots of Q. And you see that Q doesn't have a root. Q doesn't have a root here because we assume it's on the top, on the upper side of this horizontal axis. So maybe the roots are somewhere here. And I mean, they must be far away from alpha plus 1 because the roots are continuous functions of, they can be, they can like jump like that, right? It's continuous functions. So it means that when t is very large, the roots are somewhere here of PT maybe. In particular, they are not sitting in that interval alpha plus 1 alpha. On the other hand, as t goes to 0, right? So PT, when t actually is 0, right, you get P. So as PT goes to 0, the roots are going to kind of get closer and closer. Right, let me just show it to you in a diagram here. Right, so here's the diagram in mind. So P and Q are this polynomial that I chose. So P is the red one and Q is the blue one. And when t equals, so, and this is P minus TQ, so let me draw it. You see, initially it lies on P because t is set to 0, and it has two roots, exactly where they are right now. As t increases, you see, the two roots are getting closer and closer to each other, until at some point, what happens is that, as t grows, the roots are going to come closer and closer to the roots of Q, because TQ is the finite matter. So initially, you start with having two roots. When t is a small value, but non-zero, you have two roots inside this interval. And as you increase it, you go to 0 roots. So this means that at some point, like here, for example, in these polynomials, PT becomes a polynomial that has a complex or two complex roots. And this is in contradiction to the assumption that PT is real-rooted for everything. Okay, so far we saw two lemmas that connect interlacing and real-rootedness. So let's continue on. And maybe the third lemma will kind of explain to us why we are really looking at, I mean, given that we are looking at characteristic polynomials, why we are looking at degree n and n minus 1 rather than degree n polynomials. It just comes up more naturally in our settings. So, so let's say you are looking at an n by n real matrix, a real symmetric matrix A, and you're looking at some vector v in Rn. Now, for a parameter t in R, let's consider Pt of x to be the characteristic polynomial of A plus TV V transpose. Namely, you do a rank 1 update to A, but with parameter t, with a fixed V, and look at the characteristic polynomial. And what I want to understand is how is this polynomial related to the characteristic polynomial of A. Right? It's somewhat related to what we did when we talked about the toy example in the 2 videos ago. Okay. So what I'm claiming is that there is a degree n minus 1, that's where the n minus 1 comes from, a monic polynomial q of x, so it's monic, and degree n minus 1, such that pt of x can be written as follows. So it's the characteristic polynomial of A minus t times that polynomial q of x that I claim exists. Right? I mean, what's kind of obvious is that the characteristic polynomial of A and PT of x, which is also a characteristic polynomial, they're monic polynomial in x, they're of the same degree n. So when you when you subtract one from another, you are going to get a degree n minus 1 polynomial. That's not the surprising part. The nice thing about this lemma, and nothing surprises about this lemma, is that the dependence on t is such that the difference between these two polynomials, the new characteristic polynomial Pt of x and the old one, is just minus t times a monic polynomial in x. okay, of degree n-1, of course. So it's a dependence on T, that's interesting here. Okay, but that's an easy, I mean, that's exercise. So first of all, we can always do an orthonormal change of basis, and so we can assume that V is just the first unit vector E1, because you can just, you can do the base change, and chi of x, which is a determinant, won't change when you do the base change, right? So you can do that. It's just easier to do it like that. So the characteristic polynomial, the new one, A plus T E1 transpose now, well, what are we looking at, right? It's the determinant of xi minus A minus T E1 transpose. And xi minus A is this matrix. And T E1 transpose is a very simple matrix. That's why we change bases, because we like to work in this basis when you do work with matrices. So it has T at the top left corner and 0 otherwise, right? And now, if you are going to just open computer determinant, say using by scanning according to the first row, you'll see that you get exactly the determinant of x minus a. But for the first entry, when you work according to the first row, you have this t here with the minus here, and that will also contribute the minor obtained by removing the first row and first column. Like from here, this is 0, but from here. Right, so that's why you get x of a, the characteristic polynomial of a, minus t times a determinant, which is xi minus a, and the ones here, it means that you remove the first row and first column. And that function is clearly degree n-1 and monic in X. So lemma A and B talked about when two polynomials are interlacing, what happens. Lemma C kind of motivated our focus on degree n and n-1 polynomials, because these are the polynomials that we are going to see. And lemma D talks about common interlacing, right? It's actually one of the facts that we talked about in the previous video. So let's say that now you have a P0 of x and P1 of x. I'm not sure why I always change notation. I think that in the back of my mind, Q is degree n-1, and all the P's in the world are of degree n, but I don't know. So let's say that P0 and P1 are of degree n, and of course real-rooted polynomials, always with real coefficients, and with a positive leading coefficient. And let's assume, and that's the point, that they have a common interlacing. So here I'm kind of assuming that the interlace are kind of from the left, but it doesn't really matter. But they have a common interlacing. So there is a third polynomial R that interlaces both of them. Then what I'm claiming is that not the entire line, maybe, but the segment connecting P0 and P1 is composed only of real-rooted polynomials. Namely, for every t between 0 and 1, the polynomial q of x, which actually is not of degree n-1, so my theory about degree n-1 polynomial being q is false. But anyhow, this polynomial, which is a convex combination of these two, so it sits inside the segment connecting them in coefficient space, is real-rooted. Right, that's the fact. Maybe it's one direction of the fact that we talked about before. And the proof is kind of obvious, but we just need to understand what does it mean to have a common interlacing. So, when two polynomials interlace, it means that alpha 1 appears, and then beta 1, and then alpha 2, and then beta 2, and so forth. Now, when you have a common interlacing, and you can look at this picture, what happens is the following. So let's say alpha 1, alpha 2, and alpha n are the roots of the common interlacing of the polynomial R. So what does it mean that R interlaces both of them? Well, it means that the largest root of P0 is between alpha 1 and alpha 2, and also the largest root of P1 is between alpha 1 and alpha 2. Okay? And the second largest root of both of these polynomials lies in between alpha 2 and alpha 3, and so forth. So I'm not claiming that the roots of P0 and P1 interlace, but I'm claiming that the max root of them is in some interval, and then the second largest root of them is in another interval, and so forth. So this means that the largest root of P0 cannot be, I mean, it can be either larger or smaller than the largest root of P1, and same for the largest root of the second largest root of these two polynomials. But you can't have that the largest root of P0 is smaller than the second largest root of P1, right? Because the first two largest roots are larger than the second two largest roots, which are, as I said, these two are larger than the third largest root of these two polynomials, and so forth. So in that sense, it's almost interlacing. Interlacing is like that, and here it means they can swap pairs, but not more than that, right? Because the alpha i's, which are the roots of the third polynomial, requires them to live in a certain interval. So the two largest roots are here, and only then are the second largest root, and only then are the fourth largest root. And in each pair, they can be potentially in every possible order, but other than that, they are constrained like that. Okay, I hope it's clear. So with that in mind, the proof is kind of trivial, because, look at the picture, it's a proof by picture, really. This is P0, and this is P1, and Pt, when t is between 0 and 1, it always lies between this cone of these two polynomials, right? I don't know if it's a cone, but... Right, so, as t gets closer and closer to 1, you get closer and closer to P0, and so forth. But it's always like between these two polynomials like that. And because P1 and P0 has a root between alpha 1 and alpha 2, then we know that also Pt is going to have a root. Right? It's between these two roots. And so forth. So this gives you n real roots of Pt, which makes Pt real rooted. Or I called it Q here, which makes Q, which I should have called Pt, probably is real rooted. That's a bad name. Let me just change it already here. Why should I call it P? Q. Okay. It's actually not such a great name. The best name would be like 1 minus t. So that when you plug 0, actually that's a good name. No, it's a bad name. So when t is 0, I want to get P0, not P1. But never mind, it's irrelevant discussion. Okay, now let's recap. Because we have 2 more lemmas, and I think it's start to get heavy mentally to keep all of them in mind. So the first 2 lemmas, A and B, just say that P and Q interlace if and only if Pt is real-rooted for every t in R. And actually, in one of the directions, we also used the fact, so this is lemma A, that P interlaces Pt when t is larger than 0. That's what we'll need for the proof. So, the second lemma said, when we'll ever look at this such polynomials that have degree n minus t times degree n minus 1 polynomial, all of them harmonic. Well, that happens when you do rank 1 updates, like that. And the third lemma talked about a common interlacing. So we saw that if you have a common interlacing, then this means that the interval of real-rooted polynomials, when the interval in coefficients is connecting them is composed of only real-rooted polynomials. Okay, so we need 2 more auxiliary lemmas. And now we're getting more specific towards our needs, our polynomials. So let's say that we have a real symmetric n by n matrix A. And let's consider gamma to be a swap matrix. So a swap is just a permutation that permutes only 2 elements, keeping all of the other elements intact. So in like cycle notation, it's just an ij like that. Okay. Or some ij. Then what I'm saying is that if you conjugate A by a swap matrix, then that's a rank two updates of that particular form. So gamma A gamma transpose is A minus U transpose plus VV transpose for some U and V. Okay? Right, it has nothing to do with polynomials, but that's, I mean, we kind of understand rank 1 polynomials and what will happen to us when we are trying to connect our polynomials in segments will look like rank 2 updates like that. So this is a lemma that prepares us for that. And the proof is actually a bit nice. So let's assume that gamma is 1, 2. It doesn't really matter. You can do base change accordingly, like simple base change. So let's assume that gamma is 1, 2. And now observe, and that observe actually is not trivial. So I encourage you to try and do that. So observe that in order to do that, it suffices to prove that the difference between these two matrices, which we want to prove is VV transpose minus U transpose, satisfies two properties. First of all, the trace is 0, or the difference. And second is the rank is 2. Right, so once you have those two conditions, trace 0 and rank 2, and because of the symmetric, because A is symmetric, and therefore also gamma A gamma transpose, it means that you can cook up, but it's kind of a slightly case by case, so it's not completely trivial. You can cook up U and V such that this will hold. So I'll leave the two to verify that it is indeed suffice to prove these two things, but let's actually show that these two things hold. And that's kind of obvious. So if you look at the difference between these two matrices, then you know when you conjugate gamma A by gamma, so the first and second row change, but the rest remain the same. So you get a, you know, up to the first and second row and columns, you get just a huge zero matrix. And then in the first row, you're going to get A11 from A, but minus A22 from that, because then A22 goes to be in the first entry, top left entry. And this is actually A12 minus A21, but because A is symmetric, it's the same, so you get a 0, and same here because it's not together a symmetric matrix. And generally, right, you get A13 minus A23 and A31 minus A3, which is the same, and so forth, right? So anyhow, you can write this matrix as some number alpha, this number, and here you'll have minus alpha, 2 zeros here, and here there will be some n minus 2-dimensional vector that will appear here with a minus, and it will appear here also just lying like that, and with a minus here. And this is a big 0. All right, so this is A minus gamma A gamma transpose. It looks like that. And from here, it's kind of it's easy to see that it's a rank 2 matrix. The trace is obviously 0. So it's a rank 2 matrix. And the way to see that, maybe if you want, is that, well, I guess you need to split two cases. So if alpha is non-zero, then these two rows span all of these rows, right? Because every row here is like some B minus B and 0, and if alpha is non-zero, you can generate such vectors. And if alpha is 0, then so one row generate all of these in minus 2 rows, and then this row with 0s here, it has a 0 here, and the assumption generates the first and second row. So anyhow, it's dimension 2. The row columns, the row spaces of dimension 2, and so the rank is 2. Okay. And finally, the last lemma, which is actually an important lemma for us, it's kind of general actually, talks about how the max root function behaves, right? When you restrict yourself to a component in the manifold. So let's say you have 2-degree n real-rooted polynomials with opposing leading coefficient, and assume they have a common interlacing. So geometrically, it means that the entire segment connecting them doesn't cross the double root manifold. Then what I'm claiming is not just for the max root, actually. So for every point in between, so for every alpha, and for every j, so j equals 1 is going to correspond to the maximum root, but higher j's are going to correspond to the other roots. there exists some I, one of the polynomials, 1 or 2, such that lambda j of pi is bounded from above, but lambda j by lambda j of this alpha convex combination of these two polynomials. Right, so what I'm saying here is exactly what we wanted to have all along. I know a bound on the max root, say, but for any lambda j, if you want, of some convex combination of the polynomials, and I want to infer a bound on the corresponding root of one of these polynomials. In the previous video, we talked about the max root or lambda j function being monotone. Here, that's a weaker statement, but it suffices for us. It just says that one of the two endpoints, lambda j on that is smaller or equal to lambda j on the particular point that you have in the middle, depending on alpha. So good. So let's just prove it for j equals n or j equals 1, sorry, the max root. And the proof is by picture again. And it's actually obvious given what we know by now. Right, so what do we know? A common interlacing means that lambda 1 of P1 and P2 is larger than the lambda 2s of P1 and P2. I mean, it could be that lambda 1 of P2 is the largest, and then you have lambda 1 of P1, and then you have lambda 2 of P1. Not interlacing, but still lambda 1, lambda 2 don't have a lambda 1 of P1, P2 don't have a lambda 2 of anyone in between. That's what common interlacing means. Because the root of the common interlacing separates the lambda 1s from the lambda 2s. And so this means that if this is a picture of P2 and P1, then everything in between, so alpha P1 plus 1 plus alpha P2 for alpha between 0 and 1, is something that looks like the green curve here, something in between. And you can see, right, that this is the max root of P1 and this is the max root of P2, and the max root of the green polynomial is going to be in between. And then you can kind of proceed by induction and show it's for every j, but we are only going to use it for lambda 1 and lambda 2, maybe. Good. So as a recap, we have lemma A plus B that talks about real-rootedness and interlacing. Lemma C prepares us for the situation where we are going to look at a polynomial minus d times a polynomial of degree 1 less. Lemma D said that two polynomials have a common interlacing exactly when the segment connecting them is composed only of real-rooted polynomials, namely it doesn't cross the double root manifold. Lemma E just is a kind of an orthogonal lemma altogether that says that when you conjugate by a swap a matrix A, then you're essentially doing a rank 2 update of this form. And the last lemma said that P1 and P2 have a common interlacing, implies that you can, in particular in this case, as I wrote here, the minimum of the max roots of the two is at most the max root of the combination. Good. So in the next unit, we are going to get closer to our needs and our particular polynomials, but that is, this video set the ground and prepared all the lemmas that we are going to need in order to prove interlacing of the polynomials that we care about.